so there was one more example of an exact equation to wrap up the section. Well, what do we have? So y over x dx plus y cubed minus ln of x dy equal to 0. So number one, in order for an equation to be exact, okay, number one, it must be satisfied the fact that the partial of m with respect to y equals the partial of n with respect x. Okay, so let's find the partial of, this is m and this is n. All right, so what about it? So partial of m with respect to y. So here the derivative of y over x with respect to y is the derivative of y, which is 1 times 1 over x. That's 1 over x. And then the derivative of n with respect to x, well, y cubed goes to 0, so we differentiate negative ln of y. All right, which is going to give us, what is that? Negative 1 over x. Well, in this case, these are not equal. They're almost equal except for this negative sign right here. We got the opposite signs of them. Okay, well, so that means we need to figure out an integrating factor. Well, so we need to check both of them. Well, maybe we're lucky and the first one we end up getting it's a function of just x. Well, let's see if it works. M with respect to y minus n with respect to x over n. Okay, so let's see. So m with respect to y minus n with respect to x over big N, that equals, okay, m with respect to y, which is 1 over x, minus n with respect to x, and everything divided by n, in this case, which is y cubed minus ln of x. And actually, we can see here, so this will be 2 over x divided by y cubed minus ln of x. And in this case, not a function of just x. So we either have to get a function of only x or a function of only y. In this case, we have a combination of the two variables, all right? So let's try part B. So part B, which is the reverse in the numerator, n with respect x minus m with respect y, everything divided by m. Well, so what is that? Negative, all right? Negative 1 over x minus another 1 over x divided by m, which is y over x, all right? So let's see about this. So let's combine the fractions together. Okay, so that is negative, okay, negative 2 over x divided by y over x. Which in this case we have a complex fraction, right? I have a complex fraction. You might want to write this as a division. Well, so negative 2 over x divided by y over x. And then we can use the KFC rule for fractions. Do you know that one, the KFC rule? KFC, well, what's KFC? Let me write it at the top. KFC doesn't have anything to do with chicken, so this is keep, flip, change, right? So we keep the first fraction, flip the second fraction, and change the division with a multiplication. That's KFC. And well, we can eliminate the x's here. All right, we can eliminate them. And final answer, negative 2 over y. And in this case, this is a function of only y, right? So that's going to work as an integrating factor finally. All right. Well, no, that's not the integrating factor. That's only what we're going to substitute in the integral of the exponential. All right? So that's mu of y, which in this case, that's the e to the integral of this madness here. And with respect to x minus m with respect to y over m dy. All right? Which in this case, well, what did we get? E to the integral of negative 2 over y dy, which is e to the negative 2 ln of y. All right? So this is, well, we can cancel, first of all, basketball, e to the ln of y to the negative 2, and y to the negative 2, or 1 over y squared. That's going to be our integrating factor, right? So Finally, we got it. So here's the thing, guys. Again, in some cases, the first option works. We end up getting a function of only x right away, right the first time. Not like in this case, we had to go and check the second option. Okay, let me write the equation back again. So that is y over x dx plus y cubed minus ln x dy equals to 0. So what do? Multiply both sides by mu, which is our integrating factor, 1 over y squared, 1 over y squared. Okay? And well, that's y over y squared. Is that going to be 1 over, okay, that's 1 over xy dx, okay, plus y cubed divided by y squared right here. That's going to give us y in the numerator, simply a y. And then minus ln x, okay, divided by y squared. Okay, so that's dy equals, of course, 0, because 0 times inequality equals to 0. So that equation should be exact. And yes, we need to check again before solving the equation. We cannot just go ahead and solve it. We still need to check. So what's a partial of m with respect x in this case? Or wait, with respect y. Okay, I can't differentiate with respect y right away. All right, so actually let me rewrite this guy right here. Isn't that y to the negative 1 over x? That way we can differentiate with respect y, which will be negative y to the negative 2 over x, which is negative x over y squared. So that's the partial of m with respect to y. Now let's check the second one. Okay, let's check the partial of n with respect x. Well, we're going to differentiate all this with respect x. Well, y goes to 0. It's an additive constant, not a multiple constant. And here, differentiate. Okay, minus first of all. You might want to carry the negative first. The derivative of ln x.
The partial of m, it has to be the x on the bottom.
Oh yes, the other way, right? Oh yes. Also, thank you. Okay, thanks. So let me fix that. Okay, and well, we are going to do so negative 1 over x divided by y squared, which reduces to negative 1 over xy squared. And in this case, we can see these two partials are equal. That means we now have the total differential of some function of two variables, which will be the solution to the differential equation. Here is where we go ahead and solve the equation using partial integration. So the integral of m with respect to x equals the integral of 1 over xy dx. And well, integrating with respect to x, essentially we're integrating 1 over x, which is ln x. Actually, if it works for you, take out the y, which is a multiple constant. And that's simply 1 over y, ln of x, plus some constant of a function, which is a function of y. Either way, right? Let's have a look at the second integration here. That's the integral of n with respect to y, which is the integral of y minus ln of x over y squared dy. However, since we're integrating with respect to y, that y squared in the denominator cannot remain in the denominator. We need to move it, so we can move it to the numerator, so we can use the general power rule on it. We cannot do it while it's down here, all right? So that's y minus, I'm going to take out, well, let me do simply y to the negative 2 ln of x dy. So the integral of y, that's y squared over 2. What is that? Minus y to the negative 1 over negative 1 ln of x plus some constant that it's really a function of the other variable we actually held constant. Okay, let me make some room here. Whoops, that's not what I wanted to do. Okay, there we go. So, plus some c, which is a function of x. Well, let's clean that up. Number one, this is y squared over 2 minus minus, is that a plus? Ln of x, and then this y to the negative 1 goes down as with positive exponent. Okay, so here's where we form the solution. All right, so we're not going to combine any repeated terms. We will consolidate, we will put together. So what do we have from the first integration? Well, we got 1 over y ln of x, all right? Which is exactly the same as this ln of x y. So I'm going to highlight it with one color, with that same color. Okay, and I'm going to use a different color for other terms. How about the y squared over 2? All right. Do we have another? I think that's it, right? So let's form our solution. So f of x, y, which is 1 over y ln of x plus y squared over 2, and let that be equal to c. All right? And that's going to be our solution. And no, I don't think we can we, yeah, we could potentially solve for y for this one, but actually we could leave it like this. All right, to leave it in, we can leave it in implicit form.